can take your places. Oh yes, can somebody stop the music as well, please? Is there any way of stopping the music? We can't stop the music. Yeah, is it? Oh, it's linked to this, is it?
Yes.
Okay.
You have to close this window.
Ah, right.
The music, it will be stopped.
Ah, yes. Okay.
And where is your presentation?
Yeah,
Yes, this is.
That's the one.
Okay, this is microphone first. Microphone for you.
Okay, well, welcome to this, the first parallel session on IPv6. Just one point for questions, as this session is being streamed. If you'd like to ask questions, could you please wait for the microphone to come round? There is somebody with it, and use the microphone so that people on the internet can follow as well. So our first presentation is from Andreas Polirakis from the National Technical University of Athens in Greece. Andreas graduated from NTUA in 1999 and then obtained his MSc in Computer Science in 2001. He's now working as a network engineer for the Network Management Center at NTUA, and his current areas of interest are listed as being MPLS, IPv6 and routing protocols. His presentation is entitled IPv6 Deployment Challenges on the TERENA Infrastructure. TERENA is of course the infrastructure that connects several countries in southeastern Europe. But this presentation focuses specifically on the IPv6 deployment challenges. So I'll hand over to you, Andreas.
Thank you for the introduction. So hello, as you already heard, I am Andreas Polirakis. I'm from the National Technical University of Athens, which operates the GRNet network. And I'm going to present about the challenges that we encounter while deploying IPv6 on the TERENA network. TERENA is the Southeast European Research Network. And more specifically, I'm going to talk about the challenges that we found while trying to deploy IPv6 through the 6P technique over the carrier supporting carrier MPLS VPN that interconnects all those the TERENA NRNs. This is the outline of my presentation. I will start with a few details about the TERENA network, which are the connected NRNs, what is the physical and the network topology, and what is the carrier supporting carrier solution that was used to interconnect those NRNs, and also what was the IPv6 deployment scenarios, and why we finally choose 6P. Then I will get into some more technical details about the technologies, carrier supporting carrier and 6P. I will start with some NPLS and MPLS VPN basics, because both carrier supporting carrier and the 6P resemble to MPLS VPNs. And then I will briefly introduce each of the two technologies. Finally, I will talk about how we managed to deploy 6P over the carrier supporting carrier VPN for the TERENA network. What was the idea and how the entire architecture works, how the MPLS labels are distributed, and how packets are forwarded. Finally, I will give you some configuration and troubleshooting screenshots. And of course, I will conclude the presentation. So let's start with the TERENA network. The TERENA is the Southeastern European Research and Educational Network, which started in January 2004. The connected NRNs was GRNet in Greece, AMRES in Serbia and Montenegro, ISTF in Bulgaria, MARNET in Fear of Macedonia, INIMA in Albania, and BIHARNet in Bosnia and Herzegovina. BIHARNet was never connected due to non-technical reasons. And since the beginning, the picture has changed a little bit because ISTF has now has a direct connection with ZANT, so it has left Siren. Anyway, with the upstream for Siren is GRNet itself, and the upstream for GRNet is ZANT. And in case the primary link, the link of GRNet with ZANT fails, there is a backup connection through RoEduNet to ZANT. The physical topology of the network is the following. Every one of those NRNs has a local connection to an international ISP, which is at a globe. The connectivity of all those sites is achieved via a carrier supporting carrier MPLS VPN. The carrier supporting carrier is a special type of an MPLS VPN. We'll see more details later. But what you need to keep in mind is that CSE is a layer 3 VPN, not a layer 2. So we cannot carry layer 2 frames in it. Through this technique, the resulting layer 3 topology is a full mesh among all the NRNs. So Siren is an academic network, and from the very beginning, the NRNs started requesting IPv6 connectivity. So we started examining the various alternatives for IPv6. Unfortunately, native IPv6 was ruled out by the topology. The carrier network was not dual stack, so we couldn't provide native IPv6. But even if it was dual stack, IPv6 does not work over MPLS VPNs and moreover over carrier supporting carrier VPNs. The second solution was IPv6 over IPv4 tunnels. This is a simple solution. It has been tested a lot in the past. We know that it works. This is the good news. On the other hand, you know that MPLS tunnels is not a very elegant solution. It has a big complexity because it requires 2 at n connections. But at least for Siren, the number of the peers was not very high. And of course, some features that we would like would not be supported with the tunnels, like IPv6 QoS. So we started examining our last resort, which was the 6P technology. 6P is an MPLS-based technology that allows an ISP with an MPLS IPv4 core to provide IPv6 connectivity to its clients by upgrading only the edge routers to dual stack. This looked like a little bit with our case because we had an MPLS IPv4 backbone, which was the outer globe network, and at the edge of this network, there was the edge routers of the NRNs, which would be IPv6 capable. And if we were able to manage to implement this architecture, the entire thing would be transparent to the carrier. There would no upgrades and no configuration changes would be necessary for the carrier. And also QoS would be possible through the MPLS experimental bits. And the other good news is that even for our networks, only minor configuration changes and upgrades would be necessary. So the already in production IPv4 network would not be much disrupted. The bad news was that 6P is an architecture which is intended for interdomain use. And in the Siren case, we wanted to run 6P over different domains, and not only different, but to make things even worse, the domains were not even neighboring. The OTE globe domain was between them. And even more, we would like to run 6P over the carrier supporting carrier VPN. So you see that we're not sure at all that this would work after all. We're not sure if the MPLS labels would be exchanged correctly, if the packet forwarding would be done. The good news is that we tested it. It does work. It was not an easy thing to do. We had to set up the entire thing at the Cisco labs before in order to make all the testings and to find how exactly we should do it. But we did it, and it does work. Let's see a little bit about more details about the technologies. So let's start with some MPLS terminology. we refer as C to the customer edge router, the router on the top and the bottom of the figure. We refer as a P to the provider edge routers and as a P to the provider core routers. So in MPLS, as I hope you know, packet forwarding is based on a label which is imposed between the layer 2 and the layer 3 header in the packet. So initially, every router in the MPLS cloud, which is this blue box, create labels for all the IPv4 routes. Then these labels are exchanged with the neighboring routers through a label distribution protocol, which is either LDP or multi-protocol BGP. When a packet arrives in the network, in the MPLS network, the edge P router makes an IP lookup, and it finds the appropriate label that must be imposed in the network. Then the packet is forwarded throughout the network with one label. Each router that receives an MPLS packet looks up this label, finds the appropriate next router, and swaps this label with a new one. The penultimate hop router performs an action which is called penultimate hop popping. And instead of swapping the label, it just pops it and forwards a plain IP packet to the last router, who makes an IP lookup and forwards the packet to the appropriate interface. And let's see how MPLS VPNs work. So first of all, we must define the VPN. So this is done by declaring some interface on the edge routers as belonging to the same VPNs. So when we create the VPN, each router maintains a virtual routing table for this VPN, and it populates this table by the routes that it receives from the C router. Then the P routers exchange the information of those virtual routing tables through multi-protocol BGP. And along with these routes, they exchange more MPLS label for those VPN routes. So when a packet arrives at the MPLS domain, two labels are imposed in this packet. And the inner label is, when the packet arrives, it arrives on a VPN interface. So a lookup is made on the virtual routing table of the VPN. And the egress router is found through this lookup, and the VPN label is also found, which is the green label in the figure. And it is imposed on the packet. Then an additional lookup is made in order to find the way to the egress router. And the label for the egress router is also imposed. So we have two labels. The inner one, the green one, is the label of the VPN route, and the outer one, the red one, is the label that forwards the packets towards the egress router. The outer label is swapped while the packet is forwarding into the network, while the green label remains the same. The penultimate hop router performs PHP. It pops the red label, so the last router, the last P, receives the packet with only one label, the green label, through which it recognizes that it belongs to the VPN, and it makes a lookup in the appropriate virtual routing table and forwards the packet to the appropriate interface. So what is the carrier supporting carrier technique? Carrier supporting carrier is a small variation of the layer 3 MPLS VPN. And it is designed for ISPs that are VPN customers of other larger ISPs, like the TERENA and ARENs are customers of the international carrier. The advantage of this technique is that through this VPN, a very small, the carrier network only needs to maintain a very small routing table. So even if the clients exchange full routing table, like it happens for TERENA, the carrier only maintains a few routes that are necessary to reach all the Cs. In order for this architecture to work, we need to run MPLS between the P router on the bottom and the C router. So you see that there is also some label distribution protocol there, through which the C router receives the routes and the labels through which it will reach all the other Cs. So when a packet arrives at the carrier supporting carrier C, also what is not in the figure is that the Cs have to speak a multi-hop BGP and exchange routes. So when a packet arrives at the carrier supporting carrier C, it knows the BGP next hop for the packet, which is the C on the top, and it just imposes the purple label to reach this router. So when the packet is forwarded to the PE, this router just pops the purple label of the carrier supporting carrier VPN, and it replaces it with the two labels of the VPN and the other one, the red one, that forwards it towards the exit. And the rest is exactly as in the VPN architecture that we saw before. The red label is swapped, the green label remains the same. The 6P technology is pretty similar to VPNs as well. How it works? First of all, what it is. As I said before, 6P is a technique that allows a provider to provide IPv6 to its customers by upgrading only its edge routers. So the core is only IPv4, and it has to run MPLS. So 6P is pretty similar to the MPLS VPNs that we saw before. The difference is that the inner label, the orange one, does not refer to the VPN routing table, but to the IPv6 routing table. Apart from this difference, it's pretty much the same. Some other small difference is that, of course, 6P refers to IPv6 routes, not v4. And through 6P, the entire IPv6 routing table is exchanged. So it's not some virtual IPv6 table or a private one. It's the entire IPv6 routing table. And a small technical detail is that in order for this to work, the IPv4 addresses of the 6P routers, the P routers in the 6P terminology, these IPv4 addresses have to be mapped to IPv6 in order to serve as a BGP next hop for those routes. So let's see how we combine those two techniques for SIREN. The idea is pretty much the same. The figure on the right is the carrier supporting carrier architecture. What we see here is that we have, with the carrier supporting carrier, we have extended the MPLS from the one C to the other. The figure on the right is the 6P architecture. What we see with 6P is that if we have an MPLS domain, we can run 6P at the edge routers and let them exchange IPv6 routes. And then the network, because it is just handling labels, it doesn't care about the content of the packet. It will just forward since the appropriate labels are exchanged at the edge and the appropriate functions are done, the core network doesn't care about the actual content. It only cares about the labels. So the idea is that since we have an MPLS label, an MPLS network from the one C to the other, why don't we run the 6P from the C on the top to the C on the bottom and do something like this? So this is what we've done in SIREN. We integrated the two techniques. The 6P functionality now is installed on the Cs instead of the Ps of the 6P that would normally happen on 6P. And also 6P peers belong to different domains. And also notice that now we have a 3-label stack, not 2. But this is feasible just because there is this MPLS connection between the Ps and the Cs. So let's try to figure out how label distribution and packet forwarding is done in this figure. First of all, the two 6P routers on the top and on the bottom exchange their IPv6 routing table through 6P. So when an IPv6 packet arrives on the 6P router on the bottom, a lookup is made, and the orange label is found. Also, through this lookup, we know that the next hop address of the packet, which is the IPv6 address of the 6P on the top. Remember that this IPv6 address is the IPv4 mapped address of the router. So what the 6P router on the bottom does is it makes an additional lookup towards this IPv4 address. And because of the carrier supporting carrier technique, it finds the purple label for reaching this destination. So it also imposes the purple carrier supporting carrier label. Then the packet is forwarded to the carrier supporting carrier P router, the second from bottom up. This router finds an MPLS packet which has the purple label. It knows that it must replace this label with the green one for the VPN and the red one for the forwarding, and this is what it does. From now on, it's exactly as we saw in MPLS VPNs. The red label is swapped. The penultimate hop router pops the label, and the last router in this route, the 6P, the carrier supporting carrier P, receives a label with two labels: the green one for the VPN and the orange one for 6P. Through the green label, it understands it's a VPN route, so it pops it, and it forwards a packet with only one label to the appropriate interface. And finally, the last router examines the remaining label. It understands that this refers to an IPv6 route and makes a lookup to the IPv6 routing table. So this is more or less how the entire thing works. So if you think that, okay. So this is some screenshots to show you how simple it is after all to configure this thing. I don't want to get into the details of the commands, just the general idea. So in the 6P router, first of all, we enable IPv6. We have an IPv4 loopback, which is necessary for multi-hop BGP. We have an IPv4 link with OTGlobe, which is the carrier, and an IPv6 link with a GRNet network, which is the NRN. And also we run an IPv6 routing protocol through which the IPv6 routing table is populated. The BGP configuration, we see that we run multi-protocol BGP from the different address families. And we see that in the carrier supporting carrier neighbor, we have the send label command that implements the carrier supporting carrier. And in the IPv6 address family, we see the 6P neighbor with its IPv4 address, and also the send label command, which implements 6P. And some verification and troubleshooting screenshots. We'll go quickly through them. If you do a show IPBGP for the 6P neighbor, you can see that IPv6 MPLS capability is advertised and received. Also, if you do a self lookup for a route coming from this neighbor, you will see that the IPv4 mapped IPv6 address, and also two tags that are imposed. The outer one, which is the carrier supporting carrier tag, and the inner tag, which is the 6P. Some more troubleshooting. Let's go. The second one is more interesting. If you do no, actually both are interesting. The first one shows that the 6P label is number 30 that we saw before, and the second one is a self lookup for the 6P address, IP4 address, which is the carrier supporting carrier tag, which is 17. Okay, you can skip this. And the conclusions. In Siren, we had to use a carrier supporting carrier. This is something that the provider wanted because it would result to a much smaller virtual routing table. And for us, it was convenient because it's a scalable and flexible solution. With IPv6, we had two solutions with carrier supporting carrier, either 6P or tunnels. So 6P was more elegant, so this is why we chose it. But to the best of our knowledge, it was never deployed before over carrier supporting carrier. So we had several difficulties. We had to make a lab setup first to ensure that everything works. And it is possible, and after all, it does work, and this is possible just because MPLS is enabled between the edge router of and the NRN and the carrier. And after all, 6P is not so difficult to deploy over carrier supporting carrier. So I suggest that you may try it. And that was the end of my presentation. I don't know if you have any questions or if we have time for questions.
Time for some questions, if there are any. Okay, no questions?
Okay.
Could you tell us if you're employing the flow labels of IPv6 in your PE to C connections, or did you do an MPLS type of? How do you do the MPLS labeling? In other words, in IPv6.
How do we do the MPLS labeling in IPv6?
If you use the flow labels of the header.
Sorry,
the flow labels of the header.
No, the MPLS label is imposed between layer 2 and layer 3. So you can impose as many labels there as you want. I'm not sure if this answers your question.
Okay. If no more questions.
I have an additional question. I mean, how long have you been running this IPv6 carrier supporting carrier protocol? Do you have any data, any percentage of the traffic that goes IPv6 in Siren?
Not really. We run it, if I remember correctly, since November. Amres was the first one who got connected. Then some other peers got connected too. I'm not sure if they have any production services over IPv6. I know that at least they have a couple of web servers which I can ping, but I don't know if they have any real production services. We don't have any complaints though, so I assume that it works okay.
Or nobody's using it.
Yeah. They will use it eventually. So if there are any other questions, I will be glad to discuss it later. Okay.
A question there? Or? Okay then, well, thank you very much, Andreas. And,
Thank you very much also.
Okay, just a quick switch to the next presentation. Which is Brian. Okay, so moving to the next presentation, given by Brian Gilmore, who I'm sorry, Brian Carpenter. I'm sorry about that. Of IBM, and Brian is one of these people that probably needs quite little introduction, as he's been one of the leading internet computer scientists for many years. And since the beginning of this year, I think actually March, he's been the chair of the IETF. And prior to that, he held a number of other eminent positions, both within the IETF and also in the IAB. So his presentation today is on IPv6 multi-homing, the status of IPv6 multi-homing. This is sort of a thorny problem in the IPv6 field for a while, so perhaps there is finally a solution to offer. So over to you.
Okay, is that working? Now it's working. Oh. Hello?
Yes, it's working.
Well, he says it's working. You say it's not working. Yeah, I'll just raise it a little bit. That must be okay. Okay, so it's disconcerting because I tend to look up there to see what's on the screen, but actually it's down here. So if you see me pointing at this screen, you'll understand that I'm really pointing up there. So site multi-homing for IPv6. I want to tell you what a site is for the purpose of this talk. What is site multi-homing? What are the goals of the effort we've been making in the IETF? What are the principal difficulties? What are the choices we face, the proposed architecture, and a brief word on status. So, as far as multi-homing is concerned, a site could be practically anything. It could be a single computer. It could be an intercontinental company network covering dozens or hundreds of interconnected sites. So it's whatever you want to call it, basically, a site. It's a chunk of IPv6. In the context of the TERENA audience, probably a university which had 3 physical sites would have to decide whether it wanted to be 1 site or 3 sites for multi-homing purposes. And that might depend a bit on which ISPs they were using and what the contracts looked like with each ISP. So there's no real fixed objective answer as to what a site is. And the interesting case that we think we're going to see more of in the future, of course, is a mobile network, one that drives around. We haven't really thought very much about that in the work so far. But clearly, if the network is driving around, in some scenarios it's even driving around on a battlefield, by the way, then the question of how you multi-home it gets quite interesting. And we haven't really talked about that. So what's multi-homing in this context? It's simply a site of the kind discussed on the previous slide, which is connected to more than one ISP. It might be for reliability, that's the normal reason. It might be for load sharing. It might be that for whatever reason you decided that when things are normal you would put all your voice over IP traffic through one ISP and all your data traffic through another ISP, just to take a very simple example. The general case is that 2 or more multi-homed sites need to talk to each other. And it looks like this. So I've got a site 1 down here, and I'm only thinking about one particular host computer in that site. I've got a site 2 over here with a host computer in it. They're connected to ISPs D and C. And over here, he's connected to ISPs A and B. So you can see immediately there are 4 possible combinations of communication between those 2 hosts, according to which pair of ISPs they happen to use in each direction. Site 3 is just the same with another 2 ISPs, and of course all these ISPs speak to each other through something which, for the purpose of this diagram, I've called the internet, though of course the users think this whole thing is the internet. So that's the general case, and you have to consider not just a point-to-point communication between H1 and H2. You also have to consider the case where H1 and H2 start talking, and after a little while, H1 sends a referral to H2 saying, now you have to continue your conversation with H3 because that's where the application server actually is that you need. So the problem is generalized. I think by the time you've got to 3 hosts and 3 sites, you've got the general case. I don't think there's anything more general between 3 and infinity in this particular case. So that's the picture, and you need to keep that in your mind. If we had 2 screens, I'd put this on one of the screens and leave it there, because that's the picture that governs this whole conversation. So the working group that was set up several years ago discovered this was a hard problem, so had a typical IETF discussion and got nowhere for about 2 years, and finally came up with an RFC which contains a list of goals. Originally, it was supposed to be a list of requirements, and then we got into a mess because once you start using the word requirements, engineers tend to think of them as mathematically required, and since some of them are incompatible with each other, that didn't work, so we renamed them as goals and managed to publish the document. And this is a very short summary of a very complex discussion that took 2 or 3 years. So obviously the first goal is redundancy, so that communication can survive the failure of an ISP. And that includes the survival of the transport layer. In other words, the goal is if a TCP session is running, or a UDP session, and one of the ISPs goes down, then that session will survive. Load sharing, that's obviously a requirement. If you've got 2 ISPs and you're paying both of them good money, you would probably like to share the load between them, except when one of them is down. Protect performance, in other words, when a multi-homing event occurs and you switch from one ISP to the other, you should not see a dramatic degradation in performance. You will observe immediately that's incompatible with load sharing, because if you are fully loading both your ISPs and one of them goes down, then your capacity goes down, so you will lose performance. That's typically the kind of argument we were having when these things were called requirements. Policy support for ISP selection, because you might well have a policy choice that you wanted certain traffic to go to ISP A and certain traffic to go to ISP B. It's otherwise known as acceptable use policy in some circles. Simplicity, well, obviously we want simplicity. Minimal impact on the DNS, because we don't want to have to make big changes to the DNS just to cope with multi-homing. And this is a bit tricky. The solution has to be compatible with packet filtering, because if your ISP has ingress filtering, so only accepting packets that come from the address range that that ISP has given you, then if you start sending those packets to your other ISP who is also filtering, then things won't work properly because the packets will be filtered. Second set of goals, scalability, and above all, the dominant problem there is to avoid the BGP tables, if you know what they are, exploding, the routing tables from exploding, because the way multi-homing is very often done in IPv4 adds 1 BGP entry for each multi-home site, and that's not acceptable because it doesn't scale. Backwards compatibility with existing routers and existing hosts. In other words, if you introduce this solution into the network, it must not destroy connectivity for existing systems. So that's a first do no harm principle. Should not require cooperation between ISPs, because at least in the commercial internet, cooperation between ISPs is not something you can assume, because they're competitors, so why should they cooperate? and must not increase any security vulnerability. That's again a first do no harm principle. And the problem there is that it mustn't be made even easier to spoof source addresses or to conduct man-in-the-middle attacks on traffic or to steal a session. So why is this actually difficult? Well, the first point is scalability, because the easy way to solve this problem is the way IPv4 solves it, which is you simply have, if you think back to the picture, each of those three sites not only advertises its address through its own ISP for each address range that it owns, but also advertises itself through the other ISP for each address range that it owns. And that basically means that address advertisements no longer aggregate properly because they're being advertised through both ISPs simultaneously. And if you know anything about how BGP works, you'll know that that is a bad thing. If you're a real fan of BGP, you certainly are familiar with the site known as www.potteroo.net, run by Jeff Houston, which he plots the growth in the BGP4 tables over the last number of years. And you can very distinctly see jumps in that curve, which we are convinced are due to bursts of multi-homing in IPv4, due to people starting to connect to a second ISP, generating extra routing advertisements. So this scalability challenge basically removes the easy solution for multi-homing. There's another big difficulty, which is how do you make this solution deployable? How do you make it compatible? You can't change the socket API just to get multi-homing, because then you'd have to change, all the applications. You can't reasonably expect a legacy application to understand multi-homing. So you cannot do anything effectively above the socket layer and expect it to be of use. The third point is deployment. Like everything else in the internet, deployment has to go one step at a time. Obviously, if only one site has this technology, it can't multi-home, but as soon as two sites have the technology, they need to be able to profit from it, but without doing any damage to a third site. And the other difficulty when you start to look at technical solutions is the one I mentioned on the diagram, what we call referrals, where host 1 tells host 2, now you have to talk to host 3. And in a multi-homed context, it turns out that can be tricky because both hosts 1, 2, and 3 may each have several addresses. And how do you know which address is the valid one for this referral process? There are other difficulties as well, I think, but those are the ones that fitted onto one slide. So IPv6 does have a big advantage over IPv4. We've got enough flexibility in the address space that we are not completely constrained in the type of solution we can adopt. In IPv4, there's really no good solution to this problem because there is no flexibility in the address space. The only two choices in IPv4 turn out to be NAT, which many people will tell you is a multi-homing solution because everything's in net 10, so what do you care if the ISP address changes? And what I already talked about, which is advertising an address prefix to the ISP that it doesn't belong to. So if you get your addresses from one ISP and advertise them to another one, that can give you some degree of multi-homing, but it blows up the address, the routing tables. NAT, of course, breaks referrals, which is why most peer-to-peer deployments today actually do the peer-to-peer management at applications level and not at network level. And the other solution doesn't scale. So for IPv6, we believe we can do better. I'm going to talk about 3 approaches in very general terms. But the common feature of those 3 approaches is that if a site has several ISPs, each host will have several addresses. So in other words, the address prefix that your address is generated from, whether it's generated by auto-configuration or by DHCP, or even by typing it in, which is what apparently we have to do in this building, each address will have a prefix which comes from a different ISP. And once you do that, the concept of an address becomes a little bit fuzzy, so we started using the word locator, which is an address that is specific to a certain way of reaching you, of locating you. And that way, of course, is through the ISP that gave you that address prefix. So I'm going to find my way back to the, So if you have an address prefix from A and an address prefix from B, and site and host H1 has 2 addresses, one from provider A and one from provider B, then we consider those 2 addresses to be 2 locators for the purposes of a multi-homing exercise. So that gives us 3 possible directions. One possible direction, strangely enough, this was the one that seemed natural and normal to the router companies and to the ISPs, because it falls into their space. The routers do everything. The site egress router chooses which ISP it's going to use. The user doesn't have any choice over that. It changes the locators in the outgoing packet. And when the packet gets to the other end, the ingress router changes the locators back to their original value. That actually was first proposed in 1996 by Mike Odell, when he was still chief scientist for UUNet. And it turns out to have problems. It's not compatible with IPsec. It would probably create issues for SCTP, though of course in 1996 we didn't have SCTP. And there were other security concerns that people raised at the time, or in the couple of years following 1996, which were never really resolved. I'm not sure that they couldn't have been, but they weren't. And the other thing is that it turns out that deploying this step by step is very hard, because it creates difficulties, because you have to find out if the other site is going to use this mechanism or not. I'm a little sorry that this actually was never fully developed. I think it might have worked, but it didn't seem to have enough backing for people to fully develop it. Second choice, which strangely enough, people in the host and operating system business thought was a great solution, was to have the transport layer do everything. You don't change anything in the routers, right? The transport layer chooses the pair of locators that it's going to use. That's equivalent to choosing the ISPs, because there's an equivalence between the prefix in the locator and the ISP. But this process is completely hidden from applications. And it's also hidden from the IP layer because the transport layer tells it what to do. If you know anything about SCTP, Stream Control Transport Protocol, this is what it does. So this is already implemented in one particular new transport protocol. However, when you start to think about deployment, you realize you would have to change the transport layer globally. Everybody would have to put a new TCP stack in. If you're running DCCP, you have to put a new version of DCCP in. Oh, by the way, it doesn't work for UDP, which means a very large class of protocols, including voice over IP, wouldn't get any benefit from this. This was proposed in the Multi-6 working group, but again, there didn't seem to be enough momentum to develop it into a real architecture. Choice 3 is that the IP layer does most of it. The IP layer chooses the pair of locators. That's exactly what the transport layer was doing in the previous slide. But this process is hidden from transport as well as from applications. So transport still thinks it's getting an old-fashioned IP service. If you can make that work, it will work with UDP, and it will work with any future transport. There is a problem, which is you still have to choose the right egress router so that your packets are routed on the local network to the appropriate egress router to find the right ISP. So you may have to play some games with the internal routing protocol. But despite that and all the other difficulties that you discover when you start to make this thing real, this is the direction that was preferred by the Multi-6 working group and was proposed at the last IETF in a BOF called the Shim6 BOF. So I'm going to spend, how much longer do I have? Okay, the rest of the time on that. What's a shim? Not everybody who doesn't speak English knows what a shim is, and actually I didn't know for quite a long time. It's a thin, often tapered piece of material used to fill in a space between things. Okay. Some people would call that a wedge, but it's a bit more, it's sort of flat wedge. So Jeff Houston produced this slide. What you have here is two machines, A and B, which I think were 1 and 2 in my diagram. The sender sends to a pair of addresses, which are called ULIDs. I'll explain ULID in a moment. The shim maps that into a pair of locators. The packets flow through the network. At the other end, the mapping is reversed. So the packet you get back is the same as the packet you put in. Where this goes is in the middle of the IP layer. It goes, logically speaking, underneath IPsec, underneath fragmentation and reassembly, and underneath destination options, but it's above the actual IP forwarding layer. What's a ULID? It's an upper layer identifier. It's 2 of the set of locators, 1 for each end. So it looks like an address, it smells like an address, it walks like an address, but it's not an address because it's actually an identifier that the transport layer thinks is an address. And because it is, in fact, a valid address, you can use it for the referrals. So when host 1 tells host 2 to talk to host 3, it can use the ULID because that will be, because it is an IP address, valid when it gets to the other end. It's semi-persistent, well, because all addresses are semi-persistent. You need a protocol because these two ends have to talk to each other and agree on this mapping. That protocol has to be cryptographically secure because otherwise you will create new spoofing attacks. You need the egress router selection method. You need a failure mechanism that detects that there's a problem with one of the locators so that it can tell the shim to switch to another locator instead. If you want the transport layer to do more than just ignore this, you actually need to extend the API so that the transport layer can actually figure out what's going on. And there's no obvious problem with DNS, but we just need to clarify the way this thing interacts with DNS because it's standard practice in IPv6 that you can have a bunch of addresses for the same name. We just have to clarify how that relates to the fact that the addresses are now a set of locators, but one of them is distinguished as being the upper layer identifier. So that's really a quick rundown on the direction we're taking. The status in the IETF is that the Multi-6 working group has completed its tasks, goals, analysis, and recommended direction. The Shim6 BOF was held in March. We hope it'll be a working group in Paris. So I can't do it in Polish, but I can do it in French. Venez nombreux à Paris, and hopefully we'll make some more progress there. That's it.
Okay, there's some time for some questions. We've been waiting for this for so long. Surely there must be some questions. Okay, at the back there. Just wait for the microphone if you can. Fortunately, it's right the other side of the...
So what I would like to ask is, what I understand is that in choice 3, where the IP layer does it all, does the end host appear to have two different IPv6 addresses from different domains?
If it has two ISPs, it has two addresses, yeah, for sure. And they will both be in the DNS, but that's normal today. When you can do that
I have a comment on this. This may cause some problems with access lists. For example, suppose that I want to permit or deny a specific host. Now with IPv4, I just type in its address and I know that the traffic is filtered. With IPv6, I may if I want to allow a host or deny a host, I must type both IPv6 addresses, right?
If you are still running one of these old-fashioned firewalls at the boundary, yeah. If you're running a distributed firewall where the firewall function is actually in the end host, you could just do this at the ULID level, so you'd only have one. But that's the case anyway with IPv6 because any machine today can have several addresses. Well, they can in IPv4 for that matter, but it's more standard in IPv6.
Okay, thank you.
Okay, there's a question just here in the middle.
Yeah, one question. You mentioned that there's a protocol under design for the SCIM protocol for the negotiation between these ULIDs. Is there any idea on how seamless, how fast this can be? I'm thinking a bit on rapid changing addresses in mobility or stuff like this.
Yeah, well, there's two parts to the answer. Firstly, the idea is that because the ULID is a valid locator, you can start transmitting using the ULID. And unless you're exactly in the middle of an ISP failure, that will work. So you can overlap the beginning of the real traffic with the negotiation of the set of locators. So we hope that there wouldn't be any real-time penalty for the user because that negotiation can go on in parallel. The second point is that we really have not we've really not promised to solve the problems of how this relates to mobility. But indeed, if the site that's being multi-homed, you know, is a Boeing, no, let's be more European, an Airbus 380, right? Which is traveling at, you know, 1,000 kilometers an hour, then indeed the interaction between multi-homing and mobility is quite complex. And I don't think we're necessarily going to solve that in the first version of this problem, the first version of this solution, because it's potentially very hard for the reason you give.
Okay. If there are no more questions, then I'd like to thank Brian for his presentation. Okay, and then we move another quick change. Okay, so our final speaker of this session is Stig Venus, and luckily there's no one else called Stig in his room that I can get mixed up with. Stig has worked at Uninet since 2000, which is Norwegian NREN, mostly in IPv6 activities, but he's currently working on secondment with the University of Southampton, working primarily on the 6net project in the area of IPv6 Multicast. His presentation is entitled Interdomain Multicast Routing with IPv6, which will consider the different deployment methods used between IPv4 and IPv6, and also as well as how IPv6 Multicast is currently being deployed in European research networks.
Yeah, thanks. So, I guess Kevin has said sort of what I'm going to talk about. First of all, I would like to just give you some info about how PIM works, PIM sparse mode, just for those of you that don't know that much about it. So basically, all the interdomain multicast routing today is done with PIM sparse mode. And for IPv6, that's the only option, I think. And what's one of the key things with PIM sparse mode is that you need to have some rendezvous points, and I'm trying to explain what that is up there. So for a specific multicast group, all the routers need to agree on some rendezvous point, and packets from a source will initially go to this rendezvous point. When someone starts sending, the packets go to the rendezvous point. And also when some host joins a group, there's sort of some PIM join messages going from the host towards the rendezvous point, so the rendezvous point will know that there is someone listening and where to send the data. So the rendezvous point is a meeting place between sources and receivers, because with at least traditional multicast, the hosts don't really know about who the senders are or who the receivers are. So this rendezvous point takes care of that. This works well enough within a site as a single domain. All the routers can be configured with the same rendezvous point, so they agree on where to send the data and so on. But in general, on the internet, you don't want all the hosts on the internet to use this one single rendezvous point, one single router someplace on the internet for a multicast group, because that's a single point of failure, and which ISP should manage that router and so on. So that's sort of the key problem with the interdomain multicast. How do you avoid these single points of failure and management and so on? So let's just look at how it's done for IPv4 first. So I'm trying to just give you some basic idea here. So at this slide here, we have 4 different domains. Each of them got their own rendezvous point. The rendezvous point is this yellow disks. Then in each of these domains, someone is sending data, and the data is delivered to the local rendezvous point, and also people in the or hosts in the rendezvous in the domain joining send join messages towards the local rendezvous point. So it all sort of works within the single or each of the individual domains. But how do you actually get communication between the domains? That's yeah, that's the key of interdomain multicast. How do you sort of connect these domains? So the solution for IPv4 is to use something called MSTP. So what happens is that different domains create some MSTP peerings between them. It's not like BGP, but you can imagine that you set up BGP peering to someone, but you also might set up an MSTP peering. And what you do with MSTP is you have the same 4 domains as on the previous slide, and they have these peerings between them. You don't need a full mesh, but they need to somehow be connected. So this is one way it could be done with these 3 peerings up there. What happens is, if you look at sort of the same as last slide, someone down in the bottom left starts sending, and the data is delivered to the local rendezvous point. That's all the routers in that domain know about. Then you have someone, well, sorry. Then that, what happens with MSTP is that the rendezvous point in this domain tells all the other MSTP peers about this source, saying, I have someone sending data here, this is the source address. And this message follows the peerings throughout the internet. And so everyone on the internet, all the rendezvous points on the internet running MSTP would then learn about this source. Then when someone joins in this site or domain to the bottom right there, then what happens is, as usual, as on the previous slide, there are join messages going from the router next to the host joining all the way towards the site's or domain's rendezvous point. But because of MSTP, the rendezvous point in the site knows where the sources are. So it can send some joins towards the source. And this is called a source-specific join because it's not, well, it's going towards the specific source. So it's just for that one source. And if you have multiple sources, then you will build multiple paths to one path towards each source. And once this join messages have gone all the way towards the router next to the sender, you get data delivered back. So this is sort of the key idea of MSTP. There is a problem with this, though. It doesn't scale because when one host sends data in one small domain somewhere, you don't want to tell everyone on the internet that there is someone sending. And you also have to send these announcements periodically, so it's not good. And IETF decided not to do MSTP for IPv6 simply because it doesn't scale. So we have to do something different for IPv6. And one solution is something called embedded RP. At first it doesn't look like it solves the problem, but I hope I can explain why. So the basic idea with embedded RP is, well, I think it's a little bit clever. What you do is you create some special multicast group addresses where the rendezvous point address is encoded into the multicast group address. So let's just look at this example first. What happens is all the embedded RP addresses are IPv6 multicast addresses starting with FF7. And when a router sees the 7, it knows that this is embedded RP. And then you construct this address in a particular way, and there is this example here. So what happens is that the router first looks at these red digits in the address. And so first it sees it's embedded RP. It's global scope, by the way. Then it sees the number 40, or it's actually hexadecimal, so it's 64. That means that the next 64 bits in the address specifies a rendezvous point address. Except, in addition to the next 64 bits, there's also this bit earlier in the address, this 1, which is blue, you can see up there. So the rendezvous point address is the one you see, yeah, written there. So what happens is, whenever someone sends or sends data to this group or joins this group, a router supporting this sees this address and immediately know what the rendezvous point is. So it's very easy for all the routers on the internet supporting this to know what rendezvous point they should use. And by doing this, we can really simplify things. first of all, you can have a very large number of rendezvous points. Anyone can serve a rendezvous point. You can do it on your home router or whatever. And everyone on the internet supporting this will know your small router is a rendezvous point. So the idea is that someone hosting a multicast session, a video conference or streaming data, whatever, they use their own rendezvous point. And by picking a group address with a rendezvous point encoded in it, everyone on the internet will use their rendezvous point. And yeah, let's just see how it works. So it's sort of the same scenario as before. You have this no MSDP now, and you have these 4 domains, and someone is sending to the bottom left. And then when someone joins to the bottom right there, as before, the first router, the one next to the host, will see that, oh, this host joins this embedded RP address. So it looks at the address, finds what the rendezvous point is, and sends a join message to the next router towards the rendezvous point. And this way you create a path towards the rendezvous point. So if you remember on the earlier slide, these joins went directly to the source, but in this case they go directly to the foreign rendezvous point, or this sort of rendezvous point close to the source or owner of the session. And as soon as that happens, data can also be forwarded. So what happens in this case is that for a given multicast group, everyone uses the same RP. But it's not, I said earlier that having this single RP is a single point of failure and so on. But the good thing here is that it's the owner of the session or the sender of the data, in many cases, that will host the RP. So because of that, there's no third party. You don't need to rely on any third parties because the party running the rendezvous point is one of the parts in the communications. And you don't have a single common RP for all the multicast groups. You can actually have more or less one RP per multicast group if you want, almost. One thing I should point out, which I forgot, sorry about that, is that if you look at the embedded RP address up there, you have some black digits at the end. So in this example, you have 32 bits of multicast groups you can use for this RP. So you can have many groups per RP, but in practice, you would each site having an RP would just probably have a few groups, and you might have thousands or many more RPs out there. Believe that embedded RP solves many of the same problems as MSDP, but in a very different way, and it scales much better. You could wonder if you could do something similar to IPv4, but of course you can't embed the address like this. It's not enough bits to play with. You could do it some other way by having some protocol between all the multicast routers on the internet to sort of tell everyone that I have a rendezvous point here for this group and so on, but that's a new protocol and it's difficult to make that scale. Another thing is with IPv4 you only have like 24 bits for multicast addresses, and there's no real way to prevent collisions. If you pick some random multicast address, someone else might pick the same address. If you use IPv6 with an embedded RP, that helps with that as well, because you pick group addresses for your RP, and someone with another RP would pick group addresses with their RP. So because of that, you pick different group addresses. One technical difference from MSDP is that when you run MSDP and also SSM to the interdomain multicast for IPv4, what happens sort of out in the center of the internet between the domains is that you only have these SG joins joining specific sources. With embedded RP, you actually have so-called shared trees where you join not a specific source, but any source. So you just specify the group. that doesn't really matter that much. But one thing is that it might reduce the state in the core routers, because you don't necessarily need state per source. There's more to it than that, but I can't go into more details now, I think. There are some issues with embedded RP, though. One thing is that all the routers on the path between the ones listening and the rendezvous point, and also from the source and the rendezvous point, of course, needs to support this. So ideally, all the routers on the internet should support it, but you can, if they're sort of along the communications path, it will be okay. One issue is that when a user in one domain joins this session hosted by someone else, the rendezvous point is in this other domain, and it can make it harder to debug lots of problems. In IPv4, you always have your local rendezvous point, and well, lots of the issues with debugging PIM sparse mode has to do with rendezvous points, and you often need to check the state on the rendezvous point to figure out what is going on. So it can make it harder to debug multicast problems. One good thing is that you don't need any changes in hosts or applications. The only important thing is that you pick the right multicast group to use. One issue with that, of course, is a user shouldn't really need to know what the rendezvous point is and sort of construct these addresses. The user should just need to know which prefix or which range to pick addresses from, or just be told which address to use. But the sysadmin can give out a sheet of paper and put it on a web page or something. Or maybe you should have some ways of assigning addresses to applications, but that's another thing. One problem is, how do you control usage of your RP? And anyone anywhere on the internet can pick a group address with your RP and code it into it, and then traffic will go towards your RP. That might be a problem. One question, though, is why they should do this. It could be some sort of attack, but you can easily do attacks anyway by sending data directly to rendezvous points or directly to PIM routers. But yeah, this might be a problem. Another thing is, well, usually a multicast session has an owner, someone creating the session, hosting a video conference or something, or streaming data. And then it's natural which RP you pick. But there are some multicast sessions that don't really have an owner. Best example is something called SAP, Source Announcement, Session Announcement Protocol, which is used by SDR, for instance, if you are aware of that. The point is that in this case, you have a sort of permanent multicast session. There are always people sending or receiving or being joined to this group. And it's totally distributed. There's no one really owning this thing. So it's not obvious what the rendezvous point should be. You don't really want one single rendezvous point to be you don't want session announcement throughout the internet to go down just because the single rendezvous point goes down. So you need some other solutions for things like that. So this is being worked on. Well, then I'll say a bit about SSM. Source-specific multicast that's available for both IPv4 and IPv6, and it's exactly the same for both of them. And this really simplifies things quite a lot. You don't need any rendezvous points, and for those of you that know PIM well, there's lots of issues like with PIM registers switching between different multicast trees, and it's pretty complicated. With SSM, it's much, much easier, at least in the network. The big problem, though, is for applications, because with source-specific multicast, you need to know who the sources are. So if you have, say, a video conference, you need to know the address of all the other participants in order to communicate with them. There are also some other problems with SSM. You need support the core routers support SSM by default. It's just sort of how PIM sparse mode works. But the edge routers need to support MLDV2 for IPv6, or IGMPv3 for IPv4. You also need support in hosts, both in the operating system, and also you need support in the applications. So it's not really deployed yet. It's a lot of work to do. But SSM is a nice solution for interdomain multicast. So basically for V6, we got SSM and embedded RP, which are sort of the tools we have to play with. I'll say some words about deployment of IPv6 multicast. I guess most of you are thinking that, yeah, this is nice, but no one uses this. But it's actually getting deployed, not just for experiments, but also in production networks. IPv6 multicast is deployed in both the Xeon network and in Nordinet, and also in several NRNs already. It's not really that much serious use yet, though, but it's something to play with, and it's useful for students and so on to learn about these things. There's also a native multicast peering to Abilene from Xeon. There is a network called M6Bone, which has been around for 4 years, where people are playing with IPv6 multicast, learning, doing experiments, and so on. And in all these networks, we have been testing things like embedded RP and SSM. So we actually have, quite some deployment. Well, it's not that much, but anyway. So if you look at Europe, we have Xeon and Nordinet and several NRNs with some native peerings. There's also some dotted lines, which are tunnels up there. So this shows a bit of what's going on in Europe. So a lot of this is native, and some production networks, but also some experiments and so on going on. In the world, it looks more or less like this. Doesn't show all the details, but there's quite some interest in this. So we're sort of, this network has been around for 4 years, and it started with tunnels, and there's still many tunnels. But then we got Xeon and Nordinet and NRNs now with native multicast as well. So we're sort of migrating to native multicast, as well as adding new sites with either native or tunnels. So from the beginning in M6Bone, there's been one central RP. That was the only way of doing IPv6 multicast between the domains. This is still done, but it doesn't scale. But we have embedded RP and SSM now, which we are playing with. And it's not just playing or tests, it's also actually in use. There are some multicast sessions available, which people use. And since there's no changes required in hosts and applications, we have been able to do embedded RP tests as soon as we had support in routers. And there are tools like multicast beacons and standard things like beacon ret, whatever you can use. For SSM, there is not much available yet because you need support in hosts and change in the application and so on. But there is some things available, like a multicast beacon using SSM and some tool called SSM ping, which is a bit like ping, but you check that SSM is working. There's also some tool called SSMifier, which takes a normal application binary on at least Linux and does some tricks inserting a library between that application and the kernel, which makes the application use SSM without the application actually knowing that it uses SSM. It's a bit nice. But there's also some application called MadFlute we have been using, which is for streaming files using SSM. So, my last slide. So I hope you have seen from this that IPv6 multicast is actually being deployed, not just for tests, but also in production networks, at least academic ones. IPv6 multicast is much easier to deploy than IPv4 and also scales better. We have embedded RP instead of MSDP. The scope architecture is much cleaner. Also, there is no configuration necessary on most multicast routers. A router can support SSM and also embedded RP without any specific configuration. You just enable PIM. Of course, on the rendezvous point routers, you need to tell them that there should be rendezvous points and which address to use. So, yeah, we, as in me and the other authors, and I guess some other people, think that SSM and embedded RP are the solutions we need for IPv6, but there is still some work to be done. And especially the source announcements I talked about is one issue we're also looking at. And some people argue that SSM is all we need for interdomain multicast, and they might be right, but we'll see what happens. I guess that's all I had to say, except if you want to test IPv6 multicast, the best thing is to go to the M6 website, which are listed up there, and there's also pointers to a mailing list you can join, and you can get advice on how to deploy it. You can set up a tunnel or whatever to this place, or if you're an NRN, you should be able to get it from Xiant, or if you're a university, please ask your NRN if you can get IPv6 multicast from them. Yeah, so that's it.
Thanks, Steve. If there are any questions for Steve? Okay, question there. Just if you can wait for the microphone. It's just, yeah.
How is the vendor support coming along? Because what I've seen is this is mostly done on BSD and Linux systems. Are the vendors involved, or what are your prognosis about?
I think most of the vendors now support IPv6 multicast. You have, well, the large ones like Juniper and Cisco do it, but there are also smaller vendors like, say, yeah, Hitachi or Sixwind, or now Extreme is going to support IPv6 multicast, well, next year sometime. I think most of them do support it, or will support it very soon. So if you want to get involved, I guess the first thing is to either, well, set up some small PC to do IPv6 multicast or next to your normal routers, or you could, if you're lucky, you can upgrade one of your routers in your site and just start testing and so on in some small scale, and then evolve from there. But if you have a router supporting this, it's very easy to enable it most of the time.
Any more questions? Okay. In that case, thank you again, Stig. Okay, that brings us to the end of this session, and also to the end of the day's proceedings. But if I could remind you that there is the opening reception tonight in the National Museum, which starts at 7:30. And if you need to find where that is, you've got the little maps that come with the badges, and it's number 14